Monika Kudlinska, from the locals, who's going to talk to us about conjugacy separability of unipotent suspensions.
Amazing, thank you, Martin. Yeah, thank you so much to the organizers for inviting me. So today I want to speak about some joint work with, let's see, so Francois Damani. Sorry, if me and Martin were not chatting, I would have already written the names down on the board. Sam Hughes and then Nick Tweaken. Okay, and we were trying to study this property of being conjugacy separable for groups. So let me just start with some terminology. Okay, so a subset of a group is said to be separable if it's closed in the profinite topology. The profinite topology on G. Okay, so I'm thinking of G as just being a discrete group, and then I put the topology on G, which is generated by a basis of finite index of all cosets of finite index, let's say normal subgroups. Okay, so now we say that a group G is conjugacy separable, okay, if every conjugacy class is separable. Great. Good. So if a group is conjugacy separable, then actually automatically that group is residually finite. Why? Because, well, the conjugacy class of the trivial element of your group is just the subgroup, the trivial subgroup. So the subgroup that just has the identity in it. Okay, and as we will see, conjugacy separability is genuinely much stronger than residual finiteness. Okay, so why do people care about this property? So let's see some applications. So I'll start with some kind of classical algebraic applications. So let's say, so if I know that my group is finitely presented, and actually this is maybe slight overkill, so but let me stick with finitely presented, and it's conjugacy separable, then G has a solvable conjugacy problem. So there exists some algorithm that decides whether two elements in my group are conjugate or not. Okay, and this is kind of observation that was attributed to paper of Maltsev, and let me be a little patriotic and also put down, so there's a paper of Mostovsky from a little later that also observes this. Okay, and this is kind of the classic thing where you have your day and night algorithm. So let's say during the night, you take some two elements in your group and you're trying to decide if they're conjugate or not. So in the nighttime, you're going to try to verify that they're not conjugate. So if they're not conjugate, then conjugacy separability tells me there's some finite quotient of G where I can verify they're not conjugate. Okay, so in the night, I enumerate all my finite quotients of G, and I'm just checking to show that they're not conjugate in some finite quotient. And then during the daytime, I'm actually verifying whether that they are conjugate, if they are. So during the daytime, I can just enumerate all the potential conjugators and then check whether these two elements are conjugate. So whether when I do so if I have some two elements, G and GH and G, and I have some conjugator, and I'm just checking if G X inverse H inverse X is equivalent to the identity of my group. Okay, so I can again enumerate all the conjugates of the relators and just check for that during the day. Good, so that's kind of the classic application. There's another really nice application, which is, so now I only need to assume that my group is finitely generated and that it's conjugacy separable. And in fact, what I can conclude is that the auto-automorphism group of G is residually finite. Okay, so it gives me information about the auto-automorphism group. And this is a result of Grossman from the 1970s. Okay, now of course, if I only care about the automorphism group of G, then Baumslag tells us that it's enough to assume that G is residually finite. Okay, but actually, if I want to look at the auto-automorphism, then we need this stronger condition of being conjugacy separable a priori.
There is an extra condition, pointwise inner.
And of course, yeah. And we need something else, so we also need the fact that every pointwise inner automorphism is actually inner. So every pointwise inner auto is inner. Thank you, I should do that. Good, and okay, but okay. This is, for example, true for all cylindrically hyperbolic groups. Thank you. Good, so these are kind of two algebraic applications. So maybe more geometrically, let me just say something very vague. So the way that I came across this property was in studying profinite rigidity. So this is useful for studying profinite rigidity, and maybe let me be a bit more precise. So this is relative. That's kind of how I came across it. Geometrically. Okay, so what do I mean by this? So suppose I have a group. I want to study its profinite rigidity, maybe in some class. And I want to kind of do this geometrically, so I really think of this group as a fundamental group of some space, okay, maybe a manifold. And there, elements of the group correspond to correspond to loops in G. Okay, so based loops of the homotopy. Now, maybe I don't want to think about based loops. Maybe I want to think about free homotopy classes of loops, in which case elements are only well defined up to their conjugacy classes. Okay, so somehow this comes up, so CF, so again, I wonder how many times this paper will come up. So there's a paper of Liu about profinite rigidity of fundamental groups of three manifolds, hyperbolic three manifolds, and that's kind of where this comes up. And then we also use it in our paper with SAM for free bicyclic groups. Good. Okay, so that's kind of that. So let's go through some examples. Okay, so kind of baby example. So if G is abelian, then G is conjugacy separable if and only if it's residually finite. Okay, of course, all the conjugacy classes are just singletons. So as long as you know that your singleton 1 is separable, then you know they're all separable. So let's quickly move on. So then the first time that this term was actually coined was in a paper of Blackburn, who proved that finally generated torsion-free nilpotent groups are conjugacy separable. Like that. In the 60s, 5. Okay, and then sort of very quickly this was extended to all polycyclic groups. And this was by Remezlenikov. And let me just say there was also, so Formanek also proved this in his thesis. Okay, and then he published it a bit later. Good. Okay, so kind of some classical examples. Now, let me also put this down separately. So, let's say, so finitely generated virtually free groups. Okay, and you can start to see, so I put the virtually here, and there's a good reason why I put that here. And I will explain this in a second. So this was, so Stebe in the 1970s proved this, but only for, he only proved that infinite order elements of these groups are conjugacy distinguished. And then Dyer kind of finished it off, 79. Okay, but actually we'll come back to this paper because he proved a lot more things in here. Okay, so then let's move on to some more like low-dimensional topology examples. So Fuchsian groups, so Klein-Rosenberg, 1988, and then actually it was kind of not really written down anywhere that actually virtually surface groups are conjugacy separable, and this was something that Armando Martino wrote down in 2007. Okay, I don't know why such a long lit review for this talk. Okay, so finally, I'm skipping quite a lot of things here, but let me just now say some things that are a bit closer to the topic of my talk today. So fundamental groups of compact orientable three manifolds are all known to be conjugacy separable, and this was something that was proved by Hamilton, Wilton, Zaleski in 2013. Okay, but it was really kind of using the work that was developed earlier by Wilton and Zaleski. So they proved it for graph manifolds before this paper came out, and actually sort of came up with the methods that were useful in this paper. And I will talk more about that as well. Okay. And then, so let me just say one more, which is super, super cool. So virtually compact special hyperbolic groups are all conjugacy separable, and this was proved by Minassian and Zaleski in 2016. Okay, so by now actually we have quite a wealth of examples coming from the dimensional topology, and then things that people, type of groups that people in geometry groups theory are interested in. Great, so you might want to ask, can we combine conjugacy separable groups in some sensible way to obtain something that's still conjugacy separable? So we can do it via the free product construction. So free products of CS groups are conjugacy separable. So this is actually, this goes all the way back to this paper of Stebe. And actually also Remez-Lenikov, I think this paper. But that's kind of, well, that's sort of a general statement, but it's much harder, so harder to say things about more general graphs of groups. And kind of, you know, the cautionary tale should just be the bounce-back solita groups, right? So this is for everything. So BS 23. So this is, of course, the H and N extension of Z over Z. So so conjugacy separable group. But this guy is not even residually finite. Right, so one has to take a lot of care. But actually, there is work. There exists some work on amalgams. Oh well, I'm going to say graphs of groups. So let me just list some papers. So a lot of this work has been done by Zaleski and collaborators. So Ribas, Zaleski, Ribas, Siegel, Zaleski. And then a paper that I will come back to, this paper of Wilt and Zaleski. So this is the paper that I already mentioned something about. So it's the one where they prove that graph manifolds are conjugacy separable. And so in this paper, they give a fairly general combination theorem. So when does a graph of conjugacy separable groups give you something that's conjugacy separable? And sort of this was something that really inspired our work. Good. So from this list, you might think that, well, many things are conjugacy separable, and it's a property that's kind of nice. Well, it's not. So there are some non-examples that are quite shocking. So essentially what I'm trying to convey here is that conjugacy separability is very delicate. So first of all, we have some finely generated metabelian groups, a group that is not conjugacy separable. Okay, and it's really, so it's a group that's sort of looks very nice on paper. So it's just this split extension of two copies of the dyadic rationals by z squared. Okay, so really shouldn't be that bad. But this thing here is not conjugacy separable. And this was proved by Weifritz in 1973. Okay, so you can move away from this nice world of polycyclic groups, but not too far, and you will leave this conjugacy separability world. Okay, so even worse for people who like to think about groups as geometric things, passing to finite index subgroups or extensions is bad. Okay, so there's an example of Goriaga from 1975, who constructs a non-conjugacy separable, so finely generated non-conjugacy separable group G that contains a conjugacy separable subgroup of index 2. So there exists some H of index 2, such an H is conjugacy separable. Okay, so kind of bad. But even worse, so this example is finely generated, it's not actually finely presented, but also it doesn't have a solvable conjugacy problem. So you can actually cook up examples where the conjugacy problem will be solvable, but it will still be non-conjugacy separable. And there's a family of examples by Martino Minassian from 2012. So here, G can be taken to be finely presented. And G itself is conjugacy separable. And then there exists some finite index subgroup G such that H is not conjugacy separable. And the point is that G, H are finely presented and they have solvable conjugacy problem. Right, and actually you can find such a subgroup with any index. Good. Great. Now, so what we tried to do in this project was to add to the positive list. So we were thinking about a family of groups which are called free bicyclic. Now, a lot of people in this room have already heard me give the free bicyclic propaganda many times before, so I'm going to keep it very short today. But I'm going to just introduce some notation. Okay, so when I say free bicyclic, I always mean finely generated free. So F will always be a finely generated free group. Then an auto-automorphism of such a free group is called unipotent if the induced automorphism of the realization, so GL, is unipotent. So the induced auto. Okay, and it's polynomially growing.
GL and F?
Thank you. Thank you. Polynomially growing. If, and I'm not going to define this rigorously, but I'm just going to say, so every conjugacy class grows polynomially under the iteration of phi. Okay, so phi acts on conjugacy classes of F. It's an auto-automorphism, and you can find the shortest representative of each conjugacy class. It'll just be that cyclically reduced element, and you compute its length, and you see how that grows as I iterate phi. Okay. Good, so we're going to be thinking about the unipotent ones today, but actually they're not far. So if I take phi in out of F that is polynomially growing, then I can find some power of that guy, which is unipotent. Right. Okay, so now the groups that I'll be interested in will be the semi-direct products of these guys. Okay, so I'm being a bit relaxed here, but if I take an automorphism of F and then I change its representative in the outer class, I'm actually going to get the same group back. Okay, so I sometimes just put this here to be being a bit relaxed. So this thing will be called the free bicyclic group, and I will call that defining auto-automorphism the monodromy. Okay. So there is not a unique. So in general, there's no unique monodromy given a free bicyclic group. I can often find many different splittings as a free bicyclic group, and therefore many different monodromy maps. But that's something that we can ignore for today. So the monodromy, right? And as you see, so given that, so if I start with a monodromy that's polynomially growing, I can always pass to a finite index subgroup of my group G such that the monodromy will be unipotent. Okay. Now, unfortunately, that doesn't really help us here. But in general, you can always just make your situation a bit better and pass to that unipotent representative. Good. So again, if you're used to thinking of maybe not out of F, but maybe the mapping class groups, CF mapping class group of a surface, so a related group, then maybe you've thought about the Nielsen-Thurston classification of elements of the mapping class groups. And you know that, okay, either they're pseudo-Anosov, in which case they really grow exponentially, or, they're reducible. And it turns out that kind of the only way that you can get polynomial growth for these elements of the mapping class group is essentially if you're just doing Dane twists around disjoint curves. Okay, so in that case, your growth is actually always linear, And you can always take that corresponding suspension, that semidirect product, and kind of find a splitting as a graph of surface cross z's with z squared edge groups. Okay, so it's always, so in that case, these guys are fairly boring. I mean, there's still something to say. They're essentially graph manifolds, but for free bicyclic groups, we can actually get polynomial growth, superlinear polynomial growth. Okay, as soon as this rank is greater than 2. So, so things behave a little differently to maybe what your intuition might be. Good, so why do we look at these polynomially growing guys? Well, let me just say one more thing. So every free bicyclic group is hyperbolic relative to a family of subgroups. So let me just write these as Fi semi-direct Z psi I. So where psi I is polynomially growing for all of them. Okay, so often in many situations, you know, we have many good combination theorems for relatively hyperbolic groups, and so things reduce to studying these guys with the polynomially growing monodromies. So you can often kind of bootstrap it to the general case. So again, that's not really what's going to happen today, but often that is what happens. Good, so again, I'm not going to say my usual propaganda, but I am going to say, just tell you what are some known residual properties of such groups, free bicyclic groups. Okay, so it's classical that they're all residually finite. Residually finite. This is a result of Baumslag from the 70s. But we can actually say something, well, we can also say actually that, this is fairly new to me, so they're all virtually residually p-finite. P-finite. So if you allow passing to a finite subgroup, you can show they're residually p-finite for all primes p. And this is something that appears in a paper of a monograph of Aschenbrenner and Friedel, who are really only interested in fundamental groups of 3 manifolds, but actually the Fibert case gives you the free bicyclic case. This is 2013. And we can say something better. So in the case where we have the monodromy is unipotent and growing, then we can actually say that G is residually, so on the nose, residually torsion-free nilpotent. Sorry, residually finely generated torsion-free nilpotent. Okay, and thus residually p-finite for all primes p. Yep.
This is for finitely generated groups in universe.
Sorry?
Your group G is finitely generated in universe.
Yeah, okay, sure. Yeah, sure.
Every quotient will be finitely generated.
Okay. Thank you. Great. Good. Right, so this is something that I guess we observed in our paper. Good, so this is residual properties. You might be thinking about, sorry, is that still visible? Yeah. What about separability? So actually we know that all free bicyclic subgroups are separable. Okay, so if you take a subgroup that is free bicyclic, we know that will be closed, or that will be separable, but these guys are almost never, so G is almost never lerf. So it's almost never the case that all finely generated subgroups are separable. Good. And then I guess just one remark. So as long as, so if we're looking at the ones which are hyperbolic, then by Hagen-Weiss, they are actually virtually special, and so they are linear and all the nice things hold. Right, so linear, Q-serve, double cosets of quasi-convex subgroups are separable. So in that case, somehow there's nothing really to prove. Great. Good. Okay, so I can state our main theorem. Okay, so if I have a free bicyclic group where the monodromy is UPG, so unipotent and polynomially growing, then so first of all, well, what I was claiming, so G is conjugacy separable. And that's great, that's what we were going for. But actually, in order to prove this, you kind of really need to prove a few more things. So we actually prove that every cyclic subgroup is conjugacy distinguished. Okay, so what this really means is just the conjugacy class of this subgroup is closed, is separable, and then every double coset of cyclic subgroups is separable. Okay, so somehow we didn't care about these, and in fact, the double coset thing was much harder to prove in the end, but these were necessary in order to do this, and I will explain why in a second. Okay. Good, so what are the ideas that go into this? Right, so it's a very simple idea. So if B is UPG, then the corresponding free bicyclic group splits. So splits as a graph of groups. So it's a graph of free bicyclic groups. Okay. So the edge groups are abelian, and the vertex groups, they are just free bicyclic, but of lower complexity. So free bicyclic with UPG monodromy of strictly lower degree growth. Okay, so if you think about it, this is what happens in the case of the linearly growing mapping class groups. So your vertex groups in that case are just product, so the degree of growth goes from 1 to 0. And here it's just, now we are in, there's possibly higher degree growth, but each time we can drop down by at least 1 degree using this splitting. And I should say finally generated abelian. So, well, again, there is a reason why this has to be true.
But how do you get abelian group of rank more than 2?
Yeah. I also, as I wrote that down, I realized. Yeah, you can only get z or z squared, yeah. Oh, the trivial group. But you can't get the trivial group here anyway. Yeah, so it's essentially, so it's z or z squared. Good, and then the argument, as you would expect, is by induction on degree of growth. Good, okay, but as I said, we don't have sort of the full strength of a combination theorem that says if I split as a graph of conjugacy separable groups, I'm conjugacy separable. So something more needs to go into this. And really what we need is kind of nice profinite properties of this graph of group splitting. Again, this was exactly kind of what Wilton and Zaleski were doing in their paper. They said, if this long list of very nice profinite properties is satisfied by the splitting, then we can actually bootstrap the conjugacy separability property. And this is, it's almost what happens in our case, except for a few situations where it's not as good as we would like.
So Wilton and Zaleski use some sort of a symmetry.
Yes, yeah.
Do we have it here?
Yes. I'm about to say it, yeah. Yep. Good, so really the first thing that we need to prove is that the splitting has these nice properties and that, yeah, it's acylindrical even in the profinite sense. So, so first of all, we have that, so let me fix some notation. So let's say, so G, so this is the, let me call this the standard splitting of the UPG free bicyclic. Okay, so there are some people who would argue with me and say that's not the standard splitting, but they're not in the audience, so I'm going to call it the standard splitting. But then maybe if there are any experts in the audience, the one here that's the splitting for the superlinear growth case comes from improved train track, and the splitting for the linear case comes from the paper of Andrew Martino. It comes from the action of the outer space, for some reason. Okay, great. So first thing we prove is that the fundamental group of the graph of groups that comes from the standard splitting so induces full profinite topology on each vertex and edge group. Okay, and these are separable. Okay, so essentially what this is saying is that if I look at the closure of each of these vertex or edge groups in the profinite completion of the fundamental group of the graph of groups, that's already isomorphic to the profinite completion of G of B. And the same with the edge groups. Okay, so that's kind of this really the first thing you need. Second thing we prove is acylindricity. So the splitting. So in fact, it was already known that these splittings, the standard splittings, are acylindrical. But so the splitting G is actually also profinitely. So profinitely two acylindrical. So and this is when the degree of the growth is superlinear, and otherwise it's 4 acylindrical. Good. good, so what does it mean for splitting to be acylindrical? So here what I'm saying is just, so I think about the action of that group on the Basser tree, and I'm trying to, in order to prove it's kappa acylindrical, so kappa acylindrical, so if and only if the pointwise stabilizer of a path segment of length kappa plus 1 is trivial. Okay, so I'm not stabilizing long paths in my tree. And when I say profinitely, I mean this, but for the profinite graph of groups, or graph of profinite groups, because here it's the same actually, because of 1. Okay, and then the third thing is what I said, so the edge groups are double coset separable in the vertex groups. So again, this is kind of required for you when you're looking at your normal forms. You really want to be able to separate these double cosets. I'll talk about this in a second. And this exactly, well, this is, the edge groups are either Z or Z squared. So that comes from that result from number 3. And again, it's kind of something that can then be deduced of almost automatically, is that then they satisfy the so-called Wilton-Zaleski property. What does this mean? So if I have two incident edge groups, GE, GF, at this vertex group GV, then when I look at the intersection of their closures in the profinite completion of GFE, that is the same as the closure of the intersection. Okay. And again, by work of Ashford, it really kind of, these two really go hand in hand. Good.
Quick question. What is OW for OW for?
Oh, otherwise. Yeah. So otherwise, and really when I say otherwise, I mean the growth is linear. So 1. Yeah. Okay, and of course the degree 0 growth is just the product F cross Z. So nothing to prove that. Good. And so essentially, if you know these things, you can use the theorem of Wilton-Zaleski as soon as your splitting is profinitely 2A cylindrical. And so for the superlinear growth case, in fact, we can just now use these properties, plug them into the theorem of Wilton-Zaleski, and deduce our result. So the actual interesting work goes into thinking about the linear case, which is, I don't know, sometimes it's the boring case, in this case it's the more interesting case. And of course, actually proving the double coset separability is also something that's not particularly nice. Good. So the other thing I wanted to say, so the theorem of Wilton, the paper of Wilton-Zaleski, the combination theorem, the proof is very finite. So it uses a profinite Basset theory, which is something that we don't do. So we stay away from that. We take a different approach, which I assume actually is totally equivalent. But I don't know, that's what we do instead. It's a more hands-on approach. So let me explain it. Okay, so what do? We use fillings. So let's just go back to the abstract case of a group that splits as a graph of groups. And just for the sake of simplicity, let me actually assume that, for example, G is just an H&N extension of A over B. Okay, so it's just the fundamental group of a graph of groups with one vertex, one edge, A, B, two inclusion maps of B into A. And suppose there exists finite quotients of your edge group and your vertex group. So let me just call these bars, A to A bar, B to B bar. And suppose these quotients somehow respect this graph of group structure. So what I mean here is that, so there are some inclusion maps, J1 from B bar to A bar, J2 from B bar to A bar, such that the following diagram commutes. A1, A2, Okay, so I just want these inclusion maps to kind of be preserved as I can do the quotient first, or I can do the inclusions and then do the quotient, and it doesn't matter. Why do I insist on this? Well, actually, then there is a quotient of the whole group, G, A star B, to the group that's given by the graph of groups, where I replace each of the vertex and edge groups by that finite quotient. Okay, so now these are I1, I2, and now the inclusion maps are J1, J2. Okay, so the fact that I insisted on this, these diagrams commuting means that this really gives me a quotient. And moreover, this G bar is a graph of finite groups, so G bar is virtually free. Okay, so okay, there are other, I mean, this is not a new trick. This is a very old trick that's used a lot in the literature. And the point is that you've taken your group that's just a graph of groups, and you've turned it into a virtually free group, which you know a lot of things about. Okay, so in particular, so G bar is conjugacy separable. It has this double coset separability. It has all the nice properties that you're trying to prove for your group G. Okay, so let me just call this procedure a virtually free vertex filling. Okay. And essentially what we're trying to do is we're trying to take two elements of G that are non-conjugate, pass them through this quotient, and ask for them to be non-conjugate in here, and then you can pass to a further finite quotient, which also realizes their non-conjugacy. So what we really want to prove, so let me call this theta. We want to prove that the preimage of a conjugacy class in the quotient is just the conjugacy class of G. Right. So that's essentially all we're trying to prove here. Good. So i.e. gain control of conjugacy in the filled group.
Well, this preimage will contain the whole kernel. It can't be.
Yeah, maybe you're right. Maybe I don't really mean this. No. Let me just say to prove. Yeah. exists virtually free filling such that, or let's say for two elements which are not conjugate, there exists a virtually free filling such that their images are not conjugate. So the first thing that we show is that we have a lot of virtually free fillings at our disposal for these standard splittings. Right, so this was something that was already studied by Francois and Nick in their original paper on the linear growth case, and then we extended this to the superlinear case. So if you have this UPG, and this is a standard splitting, okay, then for any choice of finite index subgroup of your vertex group, for any vertex, I can pass to some deeper finite index normal subgroup, we call this prime GV, NB, okay, such that those quotients of the vertex groups so induce, or let's say extend, to a virtually free vertex filling. So from G to G bar, what this is. Okay, so this is in some sense a priori strengthening of this inducing full profinite topology on the vertex groups. Okay, as soon as you know that these guys are closed. Right. So we have a lot of these virtually free vertex fillings at our disposal, and what we do is we control conjugacy in vertex fillings, so via dynamics of the actions on the corresponding best set trees. Okay, so let's do this one last thing. Right, so you have your graph of groups, the original one, the standard splitting, and that guy is acting on its Basset tree, and now you have this quotient onto the filled graph of groups. So it's still a graph of groups, so it has its own Basset tree, T bar, and in fact there's a equivariant morphism sending T to T bar. Okay, so there exists a phi equivariant morphism. So morphism is just a map of trees that doesn't collapse any edge to a vertex. So it's sending vertices to vertices, edges to edge paths, but non-trivial edge paths. So there's a phi equivariant morphism of the corresponding Basset trees. Basset trees. Okay, and now essentially what you do is you kind of study case by case what's happening for the elements you're trying to show are not conjugate. So your elements in the isometry group of the tree can either be elliptic or can be loxotromic. Okay, in fact, if you're elliptic, then you're always being passed down in the quotient, you're still elliptic. And so elliptic or loxotromic. right? So elliptic is the case where the translation length is 0, loxodromic positive translation length. Okay. And maybe the first thing that you can prove, and there's then a long list of lemmas of things that you do afterwards, is to show that maybe for any finite subset S of your free bicyclic group with unipotent monodromy, I can find some virtually free vertex filling. So let's say T to T bar, such that the translation lengths of all the elements is preserved. Okay, for all gamma in S. Okay, and now because translation length is actually an invariant of conjugacy, as soon as you know you started with two elements which have different translation length, you can pass down to some virtually free group where they still have different translation length. And there's not conjugate, so then you can find a finite quotient where they're not conjugate. So this is like step 0, baby lemma, first thing you do, and then you kind of keep going, and you're looking at the dynamics, and you're trying to do all this analysis and normal forms and everything. So I think this is a good place to stop. So thank you.
Any questions?
At the beginning, you told that you started these cases because general case somewhat reduces to these cases because it's relatively distant. So what is the obstacle to get general case?
I mean, you mean why we do the polynomial growing case for this paper? No.
I understood why you do polynomial growth. I don't understand what is the obstacle to get general case out of it.
Oh, to bootstrap from unipotent to polynomial growing.
Yeah, if you have just virtually free bicyclic group.
Yeah.
So
Well, I think you can. I think you can. I didn't want to announce it here because we haven't worked through all the details. But yeah, it should be possible. It shouldn't be that much harder. Yeah. I mean, the problem is we don't have the nice splittings. We only have the splittings for the finite index of them.
So this is work in progress, or?
No. I mean, the unipotent case is done.
Yeah. But, and general?
General case, I mean, I think it's true. But yeah, I think it's true. Yeah.
Virtually or on the nose?
Sorry?
Virtually?
No, on the nose. Yeah. Yeah. So virtually, we have from the unipotent case. Yeah.
But you cannot go by road.
No, I don't have any idea for the non-polynomial growing case.
All right, so you're saying
I
in your case.
thought we were just talking about the polynomially growing case, like why?
I think Pavel was asking about the non-polynomial case.
Yeah.
Oh, for the non-polynomial, okay, I have no idea.
No, the general free bicyclic group, is it conjugacy separate?
Yeah, probably, but no, I have no idea. This is not what this paper is going to be about. Yeah, I have no idea.
And if the element is not unipotent but semi-simple?
Yeah, I have no idea. If it's still polynomial growing, then it should be fine, yeah.
Anything else? Oh, yeah, Asha.
So you're saying you don't really need Wilton-Zaleski result because you can work using this.
Yeah, I think we could sit down and do all of it through virtually free vertex fillings, but it just saves a bit of time to not do that.
Because you have to. So you're saying you have to do it anyway in degree 1 case.
So in degree 1 case, yeah, we have to do it via the virtually free vertex filling method. In the higher degree growth, I suspect we could do it using our methods as well, but we don't because it's already a 40-page. But the double Kosa separability, all of that is just using the virtually free vertex fillings because there's no combination theorem for that. But again, I sort of suspect that somehow the point of view of the profinite Bass set theory and these virtually free vertex fillings, they're kind of dual to, they're kind of very related to each other in some way. I mean, the proofs are very similar.
Yes. So let's thank Monika again and we break for lunch.